So I'm going to talk about CONQUEST, which is the DFT code that I've been developing in collaboration with various other people at UCL and at NIMS over the last 20 or so years. We've recently started changing how we describe it. We now call it large scale and linear scaling DFT, because that actually reflects better exactly what we do with it. So I'll take us through a rough description of how it works, and then eventually after that I'll talk about some of the more recent applications. So large-scale DFT is something that I think we need to think about more carefully. Calculations that can be squeezed into a little box of sort of somewhere between 100 and 1,000 atoms have become the norm in the DFT community. And there are significant problems with that. There are much larger scale problems we need to think about. We need to think about defects, so dislocations and surfaces. We need to think about long-range effects, like things like strain and electrostatics, realistic concentrations. So doping semiconductors, you need sort of 1 to 50,000 in silicon to avoid the metal insulator transition there. Biomolecules, as Jochen was just saying, get very, very big indeed, and self-assembled structures on surfaces. We need to model these problems. And of course, you have to ask the question, how many atoms do we need? And there's always going to be a balance here. So you've got the balance between efficiency on the one hand, where fewer atoms and a representation of the problem works, and accuracy, where you need more atoms and it's more realistic. And the size of system that you need to worry about will depend on alloy concentration, doping, the size of the problem that you're interested in. And you can sort of think about that in a slightly different way by maybe more graphically like this, where you can think about the competing requirements of accuracy and now computational cost in the bottom right there. And of course, there are other things like the functional that you're going to use, the MD time that you're using, and of course the basis size, the accuracy of the representation that you want to use there. Now, the whole idea behind CONQUEST and most of the work that's done in extending DFT to very large systems is real space locality. So this is key to parallel efficiency as well as to computational scaling. So standard DFT implementations, they're non-local. So the wave functions, the Kohn-Sham states that you calculate span the whole system. And if you're thinking about a plane wave basis set, then of course your basis functions also span the whole system. But we know that electronic structure is local. So charge density itself is local, Vanier functions, and there's an illustration there that I've taken from what I thought was a Psyche highlight, but also turns out to have been published in a paper, and I really should have put the reference there, and I apologize for not doing that. So Vanier functions, as we can see, are actually very localized, and the density matrix decays with distance in real space. So talking about the density matrix, this is actually how CONQUEST works. This is how most linear scaling methods work, is they work on the density matrix, which is a more compact way of representing the electronic structure of the system. So here's an equation that defines it formally. So it's the one particle density matrix. This is all still within the DFT language, and we're seeing here that you can define the density matrix as a sum over the eigenstates, that's psi n and psi n star, at two different points in space. So if r was equal to r prime, you would of course have the charge density. When r does not equal r prime, then you have a density matrix, which is a measure of the electronic coherence between points in space. The second line here sort of suggests exactly what we need to know, which is that as the distance between the points gets large, so then the density matrix goes to 0. And we're going to make an approximation. We're going to cut that to 0 beyond a certain distance to get linear scaling. Now, we can't work with that previous formalism because that doesn't allow linear scaling or even good large scaling. So what we're going to do is we're going to represent it as is shown here. So these functions, phi I alpha of r and phi j beta of r prime, these are what we call support functions. They're localized in space and they're centered on the atoms. And using those functions, the density matrix K is also ranged. Now, how do we solve the density matrix? Well, we start by calculating the Hamiltonian and an overlap. And that gives us, those are always found with linear scaling computational effort. To calculate the density matrix itself, we use two approaches. One is to do exact diagonalisation, so to take those Hamiltonians and feed it into Scale-APAC, or we're also looking at the ELPA routine. That's good for somewhere up to sort of 5 or 10,000 atoms. If you want to go towards 10,000 atoms with full diagonalization, we have to use an approach called multi-site support functions that I'll introduce briefly. Beyond, well, maybe somewhere between 1,000 and 10,000 atoms, you have to go to linear scaling. And it's complementary, so you can choose the appropriate method depending on the system size while using the same code in the same basis set. And we always want to have an efficient and accurate solution. So those basis sets, let me just very briefly say that we use either the pseudo-dojo or the SG15 norm-conserving pseudopotentials. Those are extremely accurate. They work very well on the delta scale. And we generate default basis sets from those. I'm not going to go into the details. The real question that we have would be, how accurately can you do with default basis sets? And let me show you some results there. So here on the left-hand side, we have a binding energy curve for bulk germanium. So the circles of the black lines are fully converged quantum espresso calculations using the same pseudopotentials as CONQUEST. And you can see that with DZP or TZTP, so reasonably sensible basis sets, we reproduce that extremely well. And on the right, you can see a table which shows again that the lattice constant and the bulk modulus of a range of different materials is reproduced extremely well with CONQUEST basis sets. So that's reassuring. It means that we don't have to tune basis sets. We can just use the default sets and get good accuracy. And this is a piece of work by Jack Baker, who's at UCL, looking at the difference in the converged plane wave charge density and the CONQUEST charge densities. This is for PTO, lead titanate. And on the left-hand side, we have the large basis sets, and on the right-hand side, we have a much more approximate basis set. What you can see is that basically there's no difference in the charge density between the two methods, particularly once you go to large systems. And that's reassuring. It's important in the context of this kind of perovskite material to get the densities right. I won't talk in detail about this multi-site support functions. Essentially what we do is we allow the support functions to bring in basis functions from other atoms, not just the atom that the function is defined on. It allows us to use a much smaller set of support functions. It's equivalent to the number of functions you'd have in a minimal basis. But of course, they're properly adaptive. They're like localized molecular orbitals. And with this, we can go to thousands and thousands of atoms with full diagonalization. Just to mention that CONQUEST is inherently parallel. We've demonstrated that we can go to 200,000 cores. That was on the K computer in Japan. And we've gone up to about 2 million atoms so far using linear scaling. So parallelization is important. So just a couple of brief illustrations of what we've been doing with it. So this now shows silicon germanium core shell nanowires. So you've got a silicon core there on those diagrams. That's the sort of the dark blue, and you've got a germanium shell. And actually, the three highly colored diagrams are showing you the strain in those nanowires projected onto different directions. So the blue shows that the silicon is being expanded, and the red and the yellow shows that the germanium is being compressed. So we can understand where the strain is laid out. We can then also, in a variety of different ways, calculate the eigenstates. So here you can see plots of those eigenstates for the silicon germanium nanowire, and also the band structure along the axis of the wire. So you see that the topmost occupied band sits in the shell, and the bottommost unoccupied band sits in the core. Let me just show you one more illustration. This is again from Jack Baker's work on perovskites. So this is lead titanate on strontium titanate. This is very new work, so I'm only giving you a very brief overview. We're hoping to be posting a preprint soon on archive. And what we've got here is we've got a system where we've got a strontium titanate substrate, and we're putting lead titanate layers of different thickness on top. And then on the right-hand side here, where you've got the A and the B on the right, you can see that you get polarization. And in the 3-layer, which is in B at the bottom there, you can see that the film is not thick enough to get flux domains, so these kind of swirling circular patterns. But on the top, where we've got 9 layers, you can see that we've actually got full flux domains forming there. So these were calculations that used about 3,500 atoms. And you need calculations of this size in order to be able to understand this kind of complex problem. So let me just conclude. CONQUEST has been released. It's freely available in a 1.0 pre-release. It's available under an MIT license, which allows a great deal of reuse. If you're interested, you can look at the ordern.org website, or you can go to our GitHub site. And you can use exact diagonalisation up to certainly 5,000 atoms. And if you have a big enough machine, up to about 10,000. And for linear scaling, you can go up towards 1 million atoms or more. So that's basically what I wanted to say. And I'm happy to take questions at this point.
Thanks, Dave. So Mikhail has a question for you.
Yes, thank you, David. This is very interesting. I was wondering about how well linear scaling DFT performs for metals, because for these materials you have a lot delocalized wave functions, right?
Yeah, no, that's absolutely right. So all of them, the systems that I was talking about here, if you're thinking about you're thinking about a gap system. So doing metals requires a different approach. So there are a couple of codes out there that have been thinking about how to do that with metals. The most interesting to my mind is the orbital free DFT, which allows you to do very, very big systems, though there are problems there both with pseudopotentials and with the kinetic energy functionals. But yeah, as the gap decreases, the range of the density matrix increases. So of course, linear scaling becomes less effective. But what we have found is that with the exact diagonalisation going up to say 5,000 atoms, that's just as easy with metals as it is with semiconductors.
Okay, Christopher has a question for you.
Hi, David. Thanks for your introduction. So I was just wondering. I know there exist other linear scaling DFT codes that have been previously developed, like OneTip. And
yeah.
I was just wondering what does CONQUEST do that is not already covered by such codes, other than being an open source code?
Okay, so CONQUEST actually predated OneTip, if you want to be technical about it. But in terms of release, I think that OneTip was released before CONQUEST. I've not seen details of scaling beyond about 30,000 atoms with OneTip, and I've not seen how well they scale in parallel. But I know that they're working very hard on that. And OneTep has the advantage that it fits very nicely with CASTEP. So just as we've demonstrated with the quantum espresso merging into, or Abinet actually, because they can both use those pseudopotentials, moving into CONQUEST, you've got that lovely kind of merging between the two different approaches. There's not a huge amount in terms of functionality that differs between these, but then you could ask the same question about Abinet and Quantum Espresso and CASTEP and all of these other codes. You know, once you've defined DFT, then to some extent you're there. So what I haven't mentioned is that CONQUEST does do MD. We do NVT and NPT with linear scaling. So if you're interested in doing, again, tens of thousands, hundreds of thousands of atoms with MD, then that's also possible.
Okay, thanks very much.
You're welcome.
Thank you, Christopher. Alex now has a question. Alex, your question. Oh.
Yeah, right. So if you are trying to deal with these very complex systems you have shown at the end, so you may need to deal with non-local functionals too.
So do you mean hybrid functionals, Alex?
Yeah, hybrid functionals. And so
yep.
Are there any ideas how to deal with that?
Yeah, so we've looked at Hartree-Fock, we've looked at exact exchange in CONQUEST. We have a preliminary implementation that scales linearly with system size. Obviously, as with all of these things, when you're wanting to do linear scaling, the first thing that you have to do is to define a range, so a physical truncation. And so you have to do that with the exchange as well. But that's in there. And in fact, if you look at the paper that I put up there at the bottom on my screen, the archive, there's some detail there about what we're doing to get linear scaling exact exchange. I wouldn't say that it's somewhere between alpha and beta status at the moment, the exact exchange implementation, but it is feasible. And it's something that we're looking to build on.